Now let us talk about light emission spectrum. Light emission spectrum. Yeah, as the title goes, there are lines that are seen as light when light is emitted from atoms. Okay? As electrons flow from the negative electrode to the positive electrode of our setup, they are going to collide with the atoms of the gas in the tube. In this case, we are talking about hydrogen gas. This collision process will lead to emission of light by hydrogen atoms or molecules. Let's talk about our setup. So you see this tube right here is this tube you see in there. Okay? And it's called a discharge tube. Now, you have a circuit. A circuit is where you have cables, and in the cables, electrons are moving, usually from the cathode, the negative side, to the anode, the positive side. So, if there is movement of electrons into the tube, and the tube has these hydrogen molecules, the electrons will collide with the hydrogen molecules in the tube, and those molecules will eventually emit light. Okay? Because when they are colliding with the electrons, they tend to gain energy. When they lose that energy going back down to their comfortable ground state, that energy is going to be lost in form of light. That's the general idea here. So assume you have the negative and positive side. So as electrons are moving into the discharge tube, as they flow from the negative side to the positive side, they will collide with the hydrogen gas in question here. It could be argon, okay, could be hydrogen, could be nitrogen, could be mercury. This collision process eventually leads to emission of light by the atoms. And if you have a photographic plate, you'll see lines. Now let's get back here. So this light is shining onto a plate that has a tiny pinhole or slit. And that light is a combination of colors that is taken into a glass prism, which is going to do what we call diffraction. In other words, the combination, this is combo of colors of light. So in other words, the combination of colors of light is going to be filtered into individual colors by diffraction. You learn that in physics, where the glass prism splits a continuum of light, a combination of light. And it's going to be split into colors. For example, you see red, you see green, and then you also see, is that blue? Then purple. Basically, the colors of the rainbow that are available in the combination of colors passing through the slit would be split. And then they strike what we call a photographic plate, which contains a chemical that will help us to visualize the colors really, really well. So this photographic plate is called a detector. So red is here, green is there, blue is there, purple is there. Notice the difference in height. That tells you that these lights have they're going to have different frequency, they're going to have different wavelength. And what did we call that? Okay, you know, speed of light is constant. is equals to wavelength times frequency. Now, if you know frequency, then that means that you're going to even have different energy. So these lights have different energies. Yeah, and that tells you that light contains packets of energy called photons, and that light contains energy that is quantized, because the energy difference here is different from the energy difference here, and it's going to be different from the energy difference right there. So let's call this delta. Delta is a difference, so let's call this delta E3. So that is the one for hydrogen. If you're looking at other elements, they will look different. Their line spectra will look different. The process is the same. You're just going to change your discharge tube. You're going to change your discharge tube. In this case, this was hydrogen gas, so probably you can swap with argon, mercury, cadmium, neon, etc. They will give you different lights. So the line emission spectrum can really help you to identify the unknown element, taking advantage of them having different combination of colors when the discharge tube is connected to a circuit. You'll see different colors in the photographic plate. Now, if we are to translate this observation to a range of wavelength, so here, down here, this is wavelength. You'll see that you have 400 nanometer, 500 nanometer, 600 nanometer, 700 nanometer. So the red will have the highest wavelength. The purple will have the lowest wavelength. Now, who's going to have the highest energy? We know that energy equals to Planck's constant times frequency. We also know that frequency itself is speed of light over wavelength. Yeah, if I'm looking for frequency here, I'll divide through by wavelength. We did this before. So frequency will be equal to speed of light divided by wavelength. So you can see that if wavelength increases, that means our energy is gonna go down. Similarly, if wavelength decreases, that means that our energy is gonna go up. So the blue and purple will tend to have the highest energy, and the red is going to have the lowest energy. So increase in wavelength decreases the corresponding energy. So this is the light emission spectrum of hydrogen gas. You have other elements here. So the first one you see here, following the same setup, just using a mercury discharge tube, is mercury. Look at the lines of mercury. They're different compared to that of hydrogen. They're different compared to that of helium. See how the colors are spread, and even the number of lines. They're different. It's going to be different to that of lithium. It's different to that of thallium. Thallium looks like he only has that one yellow line right there. These are colors of the rainbow. It's going to be different as to that observed by cadmium, and it's different to that observed in strontium. Barium will have so many lines. Look at them. There are so many. Calcium will have a bunch of purples to the left and very close reds there. Hydrogen is what we just saw. It looks like he has 4. We call that the Bose atom. We'll talk about that soon. Strontium has a quite bright yellow color, somewhere at a wavelength around here. Which wavelength is that? Okay, so down here you have the wavelengths, I believe. And then you have different light emission lines, the bright line spectra. Now next we're going to talk about the Bohr's model of the atom, and is usually referenced using hydrogen, but let's discuss and see what it talks about. Bohr's model of the atom, described in 1913 by the scientist called Bohr. So we're going to be describing this in this learning objective of the Bohr's model of the atom. So finding number 1, electron can only have specific quantized energy values. Exactly. The distances between the energy levels are not the same. You can already see what our line spectrum here did. The difference in wavelength is obvious, right? From the red to green, green to blue, blue to purple. Those are different wavelengths, meaning different energies, as I explained before in the line spectra. So now here we are saying that if you are to draw the atom will have a nucleus, and then outside the nucleus you're going to have some circles. We'll describe these as energy shells, energy levels soon, or quantum numbers. So you could have the first one as black, the second one as blue. Now I'm going to draw the red one, but at a distance a little bit. Okay, so those are energy levels. So the distance from black circle to the nucleus, that's the nucleus, must be different from the distance from the black to the blue. Okay, usually it's a little bit longer, and then it's even longer from the blue to the red. So call these energy level n equals to 1, energy level n equals to 2, energy level n equals to 3. Now if you translate this to a y-axis, so this will be n equals to 1, then probably this is n equals to 2, and probably this is gonna be equal to n equals to 3. A little bit distance. Okay, and up here they tend to be closer now as you go up. The value of n is what we're going to call the principal quantum number. The principal quantum number represents the number of shell counted from the nucleus. So if the nucleus is right in the middle of this blue circle, okay, if the nucleus is right in the middle of that circle, then the first circle after, outside that nucleus is called principal quantum number 1. The second circle will be principal quantum number 2, and the third will be principal quantum number 3, and probably we can have n equals to 4, you can have n equals to 5. So you're counting these energy shells outwards that way, like 1, 2, 3, 4, 5, and so on, etc. They have different energies because they are moving far from the nucleus, and therefore electrons, which are usually found in these energy levels, will have their own different energies. So this electron in n equals to 1 is going to have a different energy value compared to an electron in n equals to 2. And n equals to 2 will have a different energy value compared to an electron in n equals to 3. So rule number 1, electrons can only have specific quantized energy values. It's quantized because they are not continuous, they're in chunks. Okay, so now they're in steps, so it's quantized. So now there's this other rule right here, that light is emitted as electrons move from one energy level to a lower energy level. So I'm going to edit this and let it read that light is emitted as electron move from one higher energy level, from one higher energy level to a lower energy level. Okay, so let's focus here on the right. So if an electron is at n equals to 3 and it's dropping back down to n equals to 2, since he previously had high energy and is dropping down to a lower energy, where do you think that energy will go? That energy is gonna be lost. Okay, so energy is gonna be lost, and typically it's lost in form of light. Therefore we call that emission. So light is emitted as electrons move from one energy level to a lower energy level, and it's the process here for the line spectrum. Once the electrons strike the molecules in the discharge tube, like hydrogen gas tube, the molecules get excited to a higher energy level, and then momentarily they will drop back down to a lower energy level, and they release light. Now, depending where they were in the energy levels, they can release the red, emit the red, the green, the blue, or the purple. Okay, because the energy is quantized. That is why we are having these different colors emitted. So as an electron is moving from a higher energy level like n equals to 3 to a lower energy level n equals to 2, the energy is lost and it's gonna be emitted in form of a photon, or what we can say in form of light. And usually this is a process that happens whenever you are looking at a fluorescent material. Now there's an equation that helps us to calculate the energy lost between the energy levels. Okay, so like we've said, if the y-axis is energy and you are emitting from n equals to 3, let's say, to n equals to 2, here you have n equals to 1. Probably you're going to call that the ground state. Okay, so if you want to find the difference here in energy, you can do so by using an equation. Okay, however, if you want to find the energy of a specific energy level, this equation can be used. But if you're doing the difference, then you will subtract two of those, and the formula you're going to get is this one right here. This is gonna give you the change in energy between energy levels. Okay, so the difference, delta, is just the difference. The triangle is the difference in energy between two energy levels, is given by this equation, where RH is called the Rydberg constant. Okay, so for now, talking about a specific energy level, if you're looking at the energy level number 3, so n equals to 3, if you want to find the energy for that level, it will be negative of the Rydberg constant RH multiplied by, or parentheses, 1 over 3 squared, where n equals to 3. This will give you the energy value of the energy level n equals to 3. Okay, see, where n is, we just put 3. Where n is, we just put 3. Similarly, if you're looking at the energy level equals to 2, you'll put 2 here, and you put 2 there, and you'll find the equivalent energy value for that. The Rydberg constant, which was derived mathematically by Rydberg, the scientist, is 2.18 times 10 to the power 18 joules. So like I said, there's a calculation of the energy, specific energy level, and there's a calculation of the difference in energy levels. There's a calculation of energy, which is the difference in energy levels. For example, N3 and N2. And for that, you don't use this one. This one is for a specific energy level. This is for a specific energy level. You don't use that. If you're comparing the energy difference between two energy levels, you'll have to use this one, where now you see this is the initial energy level, this is the final. Okay, so this will be the formula to use. Now let's look at a series of energy transitions in the hydrogen atom. Now if you have an electron, on n equals to 1, that is what we usually call the ground state, the most stable state where an electron will want to be, closest to the nucleus. So the nucleus is somewhere here. Then you have the first circle, you have the second circle or energy level, third. So this is n equals to 1, ground state, n equals to 2, n equals to 3, and then n equals to 4. I'm not drawing the complete circle, just part of the circle. So n equals to 5, energy level n equals to 6. You can see that the energies are in stairs, in levels, so energy is quantized. Okay, so now suppose that you have an electron either on n equals to 7. So let me use the colors here. Let's say you have it at n equals to 7, n equals to 6, or an electron is on n equals to 5, or n equals to 4, or n equals to 3, or n equals to 2. If that electron drops directly way down to the ground state, that series is going to be called the Lyman series. Okay, that emission is Lyman series. Okay, now the next one will be the Balmer series. The Balmer series is where you have an electron on either n equals to 7, 6, 5, 4, 3, but those electrons are falling and stopping at n equals to 2. So if the electron ends up at n equal to 2 and stop there, we call that the Balmer series. Then we have the Paschen series, where an electron is either on n equals to 7, n equals to 6, n equals to 5, n equals to 4, n equals to 3, and then that electron does not drop down to n equals to 2 or n equals to 1. It stops at n equals to 3. That's called the Paschen series. But if the electron is either on n equals to 7, n equals to 6, n equals to 5, and drops back down, emitting light, all these drops, they emit photons in form of light energy. So those electrons drop and they stop at n equals to 4. That's called the bracket series. Now, if you want to find the energy of the photon, that should be equal to difference in energy between energy levels. So we call that delta E, and delta E is going to be equal to the energy of the final energy level minus the energy of the initial energy level. So the final energy level is where the electron ends up, whether it's Balmer, Lyman, Paschen, or bracket, and the initial is where the electron started, usually the higher energy level. And we know that if we have to find just the energy level of the final energy shell, any specific of these lines, their energies can be found by this formula. Remember, we said that for any specific energy level, we're using this formula because you're focusing on one n level. So if you're looking at NF, n final, you're using this equation where EF is the energy of the final energy level where the electron ended up. This is the Rydberg constant. You have to have a negative, and this is the number of the final energy level. It could be n equals to 3, n equals to 6, n equals to 7. You square it. Do the inverse of it. Now you do the same thing for initial. Do the same thing for initial. Now remember how we say that the energy of the photon is the change in energy, and it's always EF minus EI. So subtract equation B, subtract equation A, from equation B. If you do the subtraction of EF minus EI, these two, they will give you this equation, which is very important. So your goal is to remember that final equation that is used to find delta E. So for example, if this is n equals to 1 and this is n equals to 2, n equals to 1 is going to be equal to my n final. N equals to 1 would be my n final. N equals to 2 is going to be my n initial, where the electron started. So here n equals to 1 will be my n final, where the electron ended up. N equals to 2, if the electron starts from n equals to 2 and dropping down, emitting a photon, okay, photon released, light emitted, n equals to 2 is gonna be my n initial. Now, so if I know that n equals to 2 is n initial, so my n value here will be 2 and my n value here will be 1. N final is the n equals to 1. I know my Rydberg constant, which is this one given here, 2.18 times 10 to the power minus 18 joules. Therefore, I can solve for the energy of the photon, delta E. And that's what we're going to be doing. So remember again, any difference between two energy levels is what we are calling delta E, and it's going to be equivalent to the energy of the photon released. When an electron drops from high energy level to low energy level, a photon of light is going to be released. We said that in our summary in an earlier slide here. Point number 2, light is emitted as an electron moves from one higher energy level to a lower energy level, and that light is emitted in form of photons, and the energy of the photon can be found by calculating delta E using this last equation shown down here. Okay, this equation. So in summary, we know that light energy is quantized, or we can say energy is quantized, and it goes from level to level. So if this is a staircase, call this n equals to 1. There's gonna be a big difference in energy delta E. So that's the quantization, cutting energy in chunks. So this is n equals to 2, and then this is gonna be another change in energy. So let's call it this delta E1, this is delta E2, and then we get to n equals to 3. This is n equals to 4. You call this delta E3, and then n equals to 5. Call this delta E4. So you see that the changes in energy E1 is not equal to change in energy E2, is not equal to change in energy E3, is not equal to change in energy E4, is not equal to change in energy E5 if you go that far. Okay. Now, if an electron is dropping from n equals to 5, assume this is an electron, assume that's an electron and is dropping down. So as he drops down, he loses energy of different amounts, right? Because our delta E's are different. So he loses energy of different amounts, going down. So energy is in packets, has different amounts, different values. Energy is quantized. Let us do problems involving this equation, delta E equals to Rydberg constant, parentheses, 1 over n squared initial minus 1 over n squared final, to determine the energy of a photon. Remember, energy of a photon equals to delta E. Delta E is the difference in energy between energy levels. Example 7.4. What is the wavelength of a photon of light in nanometers emitted during a transition from energy level n equals to 5 state to the energy level n equals to 2 state in the hydrogen atom? So we have to understand what's happening here. Assume the y-axis is energy. This is energy level 1, probably energy level 2, n equals to 3. They usually come close and close when they go up there. So an electron right now is on energy level 5 and is dropping all the way to energy level 2. And as it does so, he is going to emit a photon or a light of a given energy. And that light of given energy is going to have a given wavelength. And that wavelength has to be reported in nanometers, and that's what we need. Remember that energy is Planck's constant times frequency, but frequency is speed of light over wavelength. So the same energy is Planck's constant times speed of light over wavelength. So yeah, energy is related to wavelength. So if we can find delta E in the red, as the electron drops from n equals to 5 to n equals to 2, there's going to be a change in energy delta E. So we need to find that change in energy delta E as we move from n equals to 5 to n equals to 2. So I know that delta E is equals to Rydberg constant times the difference of inverse of n squared initial state or energy level minus the inverse of n squared final energy level. So this is the formula. And so that's gonna be our step number 1 to find delta E. So once we find delta E, we should be able to find the desired wavelength. And the desired wavelength is gonna most likely be in meters. We'll convert it to nanometers. That is our strategy. So my Rydberg constant is 2.18 times 10 to the power negative 18 joules. And then my initial energy level is 5. So I'll say 5 squared. That's where the electron starts, and then it drops to n equals to 2. So 2 squared. So I'm just plugging in the value of n's, n initial, n final. I here stands for initial, F here stands for final, and I see I'm given NF and I. Okay. So all that is left is for me to do the math. I'll firstly do what is in the parentheses. This is where now your calculator skills will help you. So doing what is in here first, this is what we're going to get. So 1 divided by 5 squared minus parentheses 1 divided by 2 squared. Okay, it's giving me negative 0.21. So this one right here is gonna be negative 0.21. Then I take that number and multiply by the Rydberg constant, 2.18 exponent negative 18. So I'm getting this very small number with a negative. So let's see how many decimal places to move to after 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So my delta E here is gonna be negative 4.578 times 10 to the power negative 19 joules. It's negative here because energy is lost. When energy is lost, you kind of say the reaction is exothermic, so we put a negative, okay? But the key information is the change in energy value, this 4.578 times 10 to the power negative 19. The negative here just means that energy is lost, implying emission of a photon. Now, to three significant figures, it will be negative 4.58 times 10 to the power negative 19 joules. Keep an eye on that. Now we are done with the first part, which was determination of change in energy. So remember, by picture, we are moving from n equals to 5 level all the way down to n equals to 2 level. The difference in energy is what we are calling delta E, and a photon is emitted. Photon is lost, energy is lost, that's why we have a negative. Now, the question, it does not want the change in energy. The question wants the wavelength, okay? Remember, energy equals to Planck's constant times frequency, or Planck's constant times speed of light over wavelength, because our frequency should be c over wavelength. Okay, so we need to find this wavelength in the formula of energy. So we're going to switch gears here and say, okay, so let's draw a line. So we are going to say that speed of light equals to wavelength times frequency. We know that. Therefore, from here, if we divide both sides by wavelength, we'll find that frequency is going to be equal to speed of light over wavelength. However, we also know that energy equals to Planck's constant times frequency, but frequency is the same as speed of light over wavelength, so energy is going to be equal to Planck's constant times speed of light over wavelength. Okay, our interest is the wavelength. Our interest is the wavelength. So we are going to multiply both sides by wavelength. Okay, let's solve for wavelength. So we're going to multiply both sides of this equation by wavelength. So energy times wavelength must be equal to Planck's constant times speed of light over wavelength, which is going to be also multiplied by our wavelength. Now doing so, you will see that the wavelength and wavelength will cancel, and this side you will have energy. We could now say delta E times wavelength equals to Planck's constant times c. Now our interest is the wavelength, right? So we'll divide both sides by delta E, divide both sides by delta E. What equation do we end up with? We end up with the equation that tells us that our wavelength will be equal to Planck's constant times c over delta E. Why? The reason is delta E will cancel on the left. This is very important. That is what's gonna help us to solve for wavelength, but the wavelength solved for is gonna be in meters. So let's do that. We are on this step in our plan. So we initially calculated delta E, done. Now we need to find wavelength. and it's going to be in meters. So to do so, we'll write our formula: wavelength equals to Planck's constant times speed of light over divided by delta E. We know Planck's constant to be 6.626 times 10 to the power negative 34 joules seconds. That's usually provided in the test. And speed of light is a constant too. It's 3.00 times 10 to the power 8 meters per second. We know that. And we are dividing this through by delta E, which is negative 4.58. Now, wavelength cannot be negative. This wavelength cannot be negative. It has to be a positive number. So we are going just to use the positive value of the energy change. Okay. So we'll use the positive value of the delta E. We know the answer was negative, but that negative that just tells us that energy was lost. To find our wavelength, ignore the positive. Okay, so we'll take positive 4.58 times 10 to the power negative 19, because wavelength can never be negative. If you put negative here, our wavelength will end up being negative. We don't want that. So what is left now is to punch in the numbers. But before we do that, the SI unit of joules and joules will cancel, seconds and second will cancel. See, we are left with meters. Our wavelength will have some answer here in meters. It's a length, so meters. It's a length, so we have to give it in meters. Let's do the math. So we're going to take our Planck's constant 6.626, and then we will do exponent of negative 34, multiply it by 3 exponent 8, and then divide it by 4.58 exponent negative 19. So we are getting 4.34 exponent negative 7. So 4.3436 times 10 to the power negative 7 meters. However, we have to convert it to nanometers. Read the question. What is the wavelength of a photon in nanometers emitted during a transition of an electron from n equals to 5 to n equals to 2 in hydrogen atom? So I know that 1 times 10 to the power negative 9 meters is actually equivalent to 1 nanometer. So I'll take my 4.34 times 10 to the power minus 7 meters and multiply by my conversion factor. I want my nanometers to be numerator because that's where I'm going. So 1 nanometer is equivalent to 1 times 10 to the power minus 9 meters. Doing so, m and m will cancel. We are left with our answer in nanometers. And this answer is going to be 434 nanometers for our wavelength. So our wavelength is going to be 434 nanometers of a photon transitioning from n equals to 5 to n equals to 2. Okay, that will be the answer. The wavelength will be 434. I know I don't need a calculator here, because if you say 10 minus 7 divided by 10 minus 5 is like subtracting. When you're dividing powers, it's like you're subtracting them. So it's just like saying 10 minus 7 minus 9. That is just 10 to the power 2. So if you take 434 and multiply by 10 to the power 2, which is 100, you're going 2 steps, 1, 2. I don't need a calculator. The answer will be 434. So that's the answer.